Have you ever stared at a Kubernetes diagram and just felt your brain start to melt, wondering how on earth all those containers are actually talking to each other? Well, you're definitely not alone. It can look like a total tangled mess. So today, we're going to untangle it. We are going to demystify Kubernetes networking one simple idea at a time. Okay, so let's start with the central puzzle, the big question. We're always told that containers are these neat, perfectly isolated boxes, which, is great for security and all that. But if they're completely sealed off from one another, how does a web server container ever talk to its database container? How does any real work actually get done? And look, this isn't just some small academic puzzle. I want you to imagine a real-world application with hundreds, maybe even thousands of these containers all running across dozens of different machines. All of a sudden, this puzzle becomes this massive logistical nightmare. And this, right here, is the exact problem that Kubernetes networking was built to solve. To really appreciate the beautiful, elegant solution that Kubernetes brings to the table, we've actually got to go back to basics first. We need to see how this problem gets solved on a much, much smaller scale. We're talking about a single computer using the fundamental networking tools that are built right into Linux itself.
So the absolute core concept that makes all of this container isolation possible is something called the network namespace. The best way to think of it is like giving each container its very own private little networking universe. It's got its own connections, its own rules, the whole shebang. From that container's point of view, no other namespaces on the machine even exist.
So this is our starting point, right? We've got namespace A, maybe that's our web server, and namespace B, our database. And even though they're running on the very same machine, their namespaces keep them completely, totally isolated. For all they know, they might as well be on different planets. So how in the world do we connect these isolated little universes? Well, with a clever little invention called a veth pair. And the best way to think about this is literally as a virtual network cable. It's a digital patch cord. You plug one end into one namespace, and you plug the other end into another. Simple as that. And just like a real cable, whatever goes in one end of that veth pair comes right out the other. And suddenly, just like that, our two isolated boxes can communicate. We've just created a direct point-to-point link. This right here is the fundamental building block for all container communication on a single machine. But okay, what if you have more than two containers? I mean, connecting every single one with its own dedicated cable would be a complete mess. And that is where the network bridge comes in. Think of it like a virtual power strip or a network switch. You just connect one end of each container's veth pair to this common bridge. And now, they can all talk to each other. This is exactly what Docker's default Docker Zero Bridge does. So, we've solved networking for one machine. Piece of cake, right? But modern applications, they almost never live on a single machine. The second we add another computer to the mix, this simple, happy little model completely breaks down. And that's where things get really, really interesting. Here's the problem in a nutshell. The Docker Zero Bridge on your first machine is its own little island. And the bridge on your second machine, it's another totally separate island. A container on host 1 has absolutely no idea how to talk to a container on host 2. The simple bridge model just doesn't scale across machines. And this is where Kubernetes walks in and just changes the game with a fundamentally different way of thinking. Instead of trying to patch together all these isolated little network islands, Kubernetes says, forget all that. I've got a new, radically simple model for how networking should work. This slide really gets to the heart of it. The old way, over on the left, meant each machine was its own island with private IPs. Getting them to talk required all this complex port mapping stuff, but the Kubernetes way on the right is just beautiful. Every single pod gets its own unique IP address across one giant, flat network. Pod A on one machine can talk directly to Pod B on any other machine just by using its IP. This one change eliminates a whole class of headaches around port conflicts and network translation. It's a total game changer. Okay, so you might be thinking, that sounds like magic, but how does it actually work? Well, the answer is the Container Network Interface, or CNI. See, Kubernetes itself doesn't handle the low-level networking. Instead, it just defines a standard, an API, and basically says to the world, hey, anybody can write a plugin that follows these rules to make my network model a reality. This makes the whole system unbelievably flexible. And because of that, we've got this huge ecosystem of CNI plugins. You've got popular ones like Flannel, which is kind of the simple, straightforward choice. Then you've got Calico, which is famous for its powerful security features. And of course, all the big cloud providers, AWS, Azure, GCP, they all have their own CNI plugins that hook directly into their own networks. They all do it a little differently, but they all achieve that same incredible goal, making that flat pod-to-pod network a reality. So we know the what, this big flat network. Now for the really cool part, the how. Let's actually trace the journey of a single packet of data as it travels from a pod on one machine to a pod on a completely different one. This is where the magic happens.
All right, here's how it works. When pod A wants to talk to pod B, it just sends a normal network packet. But before that packet leaves the first machine, this CNI plugin grabs it. It takes that original packet and wraps it inside another bigger packet. This is called encapsulation. Now this new outer packet is addressed to the other machine, node 2. When node 2 gets it, its CNI plugin unwraps it, finds the original packet inside, and delivers it to pod B. It's kind of like putting a letter with a local address into a bigger envelope with a cross-country address just to get it to the right post office.
This whole process of wrapping and unwrapping, that's what creates what we call an overlay network. It's a virtual network that's laid right on top of the physical one. And what's so brilliant about it is that from the pod's perspective, the underlying machines are completely invisible. They just see one big flat network where they can talk to anybody they want. Okay, so let's zoom out one last time and put all of these pieces together. We've seen how pods talk to each other, but that's really just one piece of the puzzle. Kubernetes networking is actually a system of layers, and each one is solving a different part of the problem. This quote right here is the perfect summary. At the very bottom, you've got the node network. That's the physical wires or cloud network connecting your machines. Laid on top of that is the pod network. That's the magic overlay we just talked about that gives us seamless pod-to-pod communication. And then on top of all of that is the service layer, which gives us a stable address and load balancing for our pods. Those three layers working together, that's the Kubernetes network. So by creating this flat, simple overlay network, Kubernetes solves that fundamental, messy problem of getting containers on different machines to talk to each other. It's a powerful foundation. But it also raises a new question, doesn't it? If Kubernetes has made this part so seamless, where does all the complexity hide now?